Hello everyone, I'm Patrick, and this is a joint work with my advisor, Chen, and our collaborators from different institutions. So here's what SpotProxy is all about. Essentially, it's a circumvention proxy architecture that is inspired by a special kind of virtual machine on the cloud, a Spot virtual machine. And using our architecture, you're able to reduce costs for hosting proxies and VMs by around 90%. You're able to have massive proxy footprint coverage by leveraging the cloud's near unlimitless resources to essentially transition to different proxies automatically across time. And in doing so, using this and other techniques, we're able to show that it's difficult for censors to block our proxies, particularly IP-based blocking. So we've heard that circumvention is important, and we also know, importantly, that proxies have been deployed in cloud virtual machines for quite some time. So here, let's go through a very simple workflow of how circumvention is done using proxies. So here we have Alice, who is in a censored region, who wants to access a blocked website, let's say Facebook. So this is blocked by a censor filter at the border of the region. So what Alice needs to do is to make use of a proxy device. In our case, this is going to be located in a cloud virtual machine. And we know that this is deployed in places like Tor and also Siphon. And what this proxy does is that it intercepts these packets from Alice and redirects it to its intended destination, in this case, which is Facebook, completing the cycle. So overall, the censor blocks packets destined to Facebook's IP address, but Alice's packets would be okay, presumably because the proxy's IP address is not blocked. And one thing to note is that there's a huge power imbalance between the censor and the censored because the censor has near limitless resources, near unlimited resources, and the censored has to rely on typically volunteers who are resource constrained. So why deploy things on the cloud, right? On one hand, it appears to be a very natural choice, given that the impact it has had on different kinds of workloads and services, not just for proxies. This includes its typically assumed pay-per-use model, where you only pay for what you use. Also includes stable performance because the cloud essentially guarantees, provides service-level agreements for performance. It also has automated provisioning because you don't have to provision physical nodes in a dedicated place. You can outsource this to the cloud. You have ease of configuration because the cloud providers strive to make virtual machines and other kinds of infrastructures very easy to deploy and use. And proxy developers often supply cloud configuration scripts for automation. Also, cloud providers dedicate a lot of resources to make sure that you have five or more nines of availability, so you can be rest assured that your proxies would stay connected. On top of that, you have customizable performance in the cloud. In terms of VM resources, you have various product classes, including dedicated virtual machines, shared virtual machines, and so on. And overall, this means that VM-backed proxies on the cloud can handle much more traffic and connections compared to a lot of different kinds of infrastructure. So there's one very important caveat, though, and this is because the cloud is very expensive. In particular, cloud virtual machines are expensive, and many charges are actually incurred even when the machines are idle. What this means for proxies is that even if your proxy is blocked, or if it's idle, no connections going on, you're still being charged money. And in particular, this includes resources like memory, compute disk resources, and also IP addresses. These are actually being charged right now in the cloud, even when you're idle. So this is evidenced by the fact that cloud costs are actually steadily increasing across major corporations, as you can see at the bottom here on the left-hand side. And also, there's a lot of wasted money in the cloud. So this has given rise to a phenomenon known as cloud repatriation, where, as you can see on the right-hand side corner, around 85% of enterprises are actually considering repatriating from the cloud, and that means moving your workloads from the cloud to on-prem infrastructures just to curb these steep expenses. This is particularly problematic for circumvention proxies, both for proxy contributors but also for the censored clients. For the former, financial strain is not uncommon, especially when dealing with usage surges. So for example, Lantern had to resort to accepting donations and using credit cards to sustain operations when they had to scale up due to usage surges. On the other hand, you could claim that, hey, let's ask censored clients to pay for this. That's perfectly fine, except for the fact that you're making it harder for clients to access the free internet. There's an increased barrier here. And this is because clients could be financially constrained. They could already be using government or NGO donations to access the free internet. Payment channels for proxies could be restricted, and also paying for VPN services could be criminalized. So what this unfortunately means is that dodgy free VPN services, for example, in Russia, are in frequent demand. And this is besides the fact that they have opaque ownership and they often harvest user data to sell them to data brokers. So for sustainable operation of legitimate VM-backed proxies, we must consider cost. Overall, this means that cloud features must be rediscovered for censorship given its uniqueness, and simply lifting and shifting proxies from whatever infrastructure you have onto the cloud falls short because of this ultra-sensitiveness to cost. So the inspiration of our paper came from this special class of virtual machines called Spot virtual machines that are available in most major cloud providers at the moment. And these Spot VMs are spawned out of cloud provider access resources just in time to maximize profit. But at the same time, they can be taken back from the user when higher paying tenant requests arrive. So the pro here is that these machines cost a fraction compared to regular virtual machines. But a con is that Spot VMs can be reclaimed at a very short notice. This dynamicity and instability is an annoyance for regular applications, but it's actually a boon for circumvention because you can kind of imagine that this fluctuation in the IP addresses assigned to these machines that you have, separate machines that you have, could actually help with bypassing blocking. So SpotProxy takes this inspiration head-on and leverages this and other features in the cloud to systematically extract their benefits for circumvention. We have 4 design goals. The first one is to minimize cost for usable circumvention. The second is to leverage the near limitless cloud resources to make censor blocking more challenging. The instability that we mentioned earlier that occurs because of the usage of Spot virtual machines would mean that we need frequent reassignments of clients to proxy instances. And we need to make sure that this does not incur any overhead. And finally, SpotProxy only relies on mostly cloud-agnostic features that are available in most cloud providers that include not just Spot VMs, but also multi-NIC instances and elastic IP capabilities. So let's go through a very quick architecture and workflow overview of SpotProxy. So first, the client contacts some proxy distribution service that you can see on the right-hand side. This could be a broker as in used by Snowflake or something else. This is forwarded to a controller which would use some arbitrary proxy assignment mechanism. We have something integrated into SpotProxy right now. And then retrieve some proxy identifier within its fleet and sends it back to the client. From here, the client connects to its assigned proxy, which forwards the request to a NAT device, which preserves a stable vantage point for its intended destination. And this completes the cycle for the initial connection. After this, our rejuvenator would kick in, and what it essentially does, among other things, would be to continuously refresh the fleet by finding the cheapest possible instances within various cloud providers and within different regions and availability zones and so on. And it also embraces cloud provider-induced Spot VM reclamation, and in doing so, allows it to accumulate a massive proxy fleet over time. And this, in turn, allows it to counter IP-based blocking. Finally, the controller takes in these rejuvenation actions and actually performs reassignments based on that. The relocator is the one that actually realizes these assignment decisions made by the controller And what it does is it migrates clients to new proxies. And there are various reasons you would need to do this, including fleet composition changes. One key important point is there are no actions required by the client. For more details, please refer to our paper. So we've implemented our relocator on Wireguard. We wrote a management layer around Wireguard to enable this. And for Snowflake, we have done this using minimal targeted source code modifications because Snowflake already has a very well-integrated ecosystem. And our rejuvenator currently supports AWS using its official SDK for Python. We've conducted extensive evaluations using a live network testbed with EC2 virtual machines. And we've also performed a circumvention efficacy evaluation using a state-of-the-art sensor simulation platform that you can find more details in the paper. So one important thing that we evaluated is instance cost savings compared to various baselines across. And here we see a sampling of this across a few selected months. So in green, what you see is the very, very simple base case where you're using regular virtual machines without any changes. Very expensive. In yellow, you see the base case where you're using just normal Spot virtual machines without any changes. And in orange, you see the case where we have the rejuvenator kicking in and changing the instances across time. And this achieves significant cost savings. In blue, you see the lowest cost that we were able to achieve by adopting a separate feature within the cloud, which is multi-NIC instances. And in here, what we're doing is basically assigning individual proxies to individual NICs within the same machine, thus lowering cost. So overall, we can provide significant cost savings. One more thing that we evaluated among other things is relocator overhead. So we did this by evaluating it on a couple of different applications with different characteristics, and here is a sampling of them. We tested both of our implementations, and as you can see, in the case with the orange dashed lines without migration, which is our baseline, and comparing this to our relocator, where you have migrations with the blue solid lines, active migration only incurs sub-second overhead, sub-second migration, and overall, this means there's negligible overhead for migration. So you can refer to our paper for more evaluations. And in summary, SpotProxy currently provides significant cost savings, cloud-native unblockability, and in our evaluation using the simulated platform, even in the most aggressive worst-case scenarios, much more so than what the original paper did, we're able to guarantee access to more than 60% of clients, even when 50% of the clients are Sybil clients, which means censored agents. We're also able to preserve seamless network connectivity and integration with AWS and 2 proxy implementations so far. We have a working prototype available on GitHub, and feel free to give it a star if you like the project. Active expansions are ongoing right now, and all contributions are welcome. And also, our prototype is functionally evaluated already, and I'm actively searching for internships. Well, thank you, and feel free to reach out for a chat. Thanks.